of Markov's inequality that you might have seen before, because it has a name, is called Chebyshev's inequality. Chebyshev's inequality is the following statement. It says that if x is a real valued random variable, and assuming it has a well-defined variance, here we're dropping the condition that x has to be non-negative. X here in Chebyshev's inequality can be anything. For all t strictly positive, the probability that x differs from its mean, e of x, in absolute value by more than t is upper bounded by the variance of x divided by t squared. So what's interesting here is that compared to Markov's inequality, this is still a statement about a random variable being far away from its default value. But you see that the decay, instead of being 1 over t, is 1 over t squared. So the two bounds are totally consistent. They're jointly true. But the fact that we have 1 over t squared for Chebyshev's inequality gives us a bit more information about how the tail goes to 0 in that probability distribution. So just for fun, let's try to prove Chebyshev's inequality together. And Chebyshev's inequality is actually a direct consequence of Markov's inequality. And we're going to show together how we can get there. So let me pull up my slides again. So how do we prove this? So we're going to make one simple and yet extremely powerful observation. And that observation is the following. It says that we can boost Markov's inequality. We can boost Markov's inequality. And what do I mean by boosting? So let's assume that we have a random variable x that takes value in some domain x. Okay, and that domain x, we're going to assume, is a subset of R because we have a real valued random variable. And we're going to consider a function. And that function I'm going to call phi. And that function is going to have the following property. It takes an input in the alphabet of the random variable x, and it goes into a domain which is always R plus. Don't get negative values. And I'm going to assume that it's non-decreasing. So if x less than y, phi of x is less than phi of y. And I'm also going to assume that it's a slightly more technical condition, that if you look at the expected value of the absolute value of phi of x, is strictly less than infinity. It means that phi is absolutely, phi of x is absolutely integrable. It's just a technical condition. Then what I'm claiming is I'm claiming that we can use that directly in Markov's inequality to make our life easier. Why? Let's do it as follows. Let's say I want to bound the probability that x is greater than or equal to t. That's the objective of Markov's inequality. Well, as I know, it is equal to the expected value of the indicator function x greater than or equal to t. But now, if x is greater than or equal to t, I know that phi of x has to be greater than or equal to phi of t. Why? Because I'm assuming that the function phi is non-decreasing. So I can multiply my indicator function by another indicator function, phi of x greater than or equal to phi of t. Okay, so that might seem a little strange, but the reason I can do this here is because this is always one if x greater than or equal to t. So you are never in a position where you would multiply by 0 if the first term, the first indicator function, is 1. Now, as a result, you have the product of two indicator functions. The first one is between 0 and 1, so it doesn't cost you anything to remove it to get an upper bound. By definition, because one indicator function x greater than t is less than 1, the expectation has to be less than indicator function phi of x less than phi of t. And what is that? This is by definition the probability that phi of x, and I think I've made a mistake here in inequality, so it is greater than phi of t. greater than phi of t. So what's happening here? I found an upper bound on that probability in terms of phi. What do I know about phi? Phi actually is a non-negative random variable. Phi of x is a non-negative random variable. So I can use Markov's inequality to phi of x, and therefore upper bound is by the expected value of phi of x divided by phi of t. So this is what I call the boosting, to get a slightly potentially better bound than Markov's inequality. And we haven't done anything. All we've said is let's use a function phi that is non-decreasing, like technical condition, and non-negative. Now the trick is, based on that observation, that you can boost Markov's inequality, you can always come up with better bounds. The trick is find phi that is actually useful, that you can analyze it. One such application that is actually not too hard is Markov's inequality, Chebyshev's inequality. So as an application of that boosting, let's consider the following. So let's consider the random variable y defined by definition as x minus e of x. Okay, so what can we say about that random variable? That random variable is non-negative. So it satisfies the condition of Markov's inequality. And therefore you can say that the probability that x minus e of x greater than or equal to t would have to be less than the expected value of the absolute value of x minus e of x divided by t. That's Markov's inequality. But now I can try to boost Markov's inequality by using the following function. I'm going to use the following function, so it's going to take value from r plus to r plus, and it's going to take x, and it's going to give me x squared. Now phi on the domain r plus is indeed a non-decreasing function because x squared is increasing on the positive real values. And so if you apply the boosting to Markov's inequality, what do we get? Based on the previous argument, we obtain that the probability that x minus e of x greater than or equal to t can be upper bounded by, now the expected value of phi of x, which would be the expected value of x minus e of x in absolute value, squared, so the absolute value doesn't matter, divided by t squared. But if you remember, the expected value of x minus e of x squared is nothing but the variance of x divided by t squared. And so that's Chebyshev's inequality. So, quite surprisingly, Chebyshev is nothing but a small boosting of Markov's inequality. But what you've gained by using Chebyshev's inequality is that the decay now has changed from t to t squared. And therefore, it's giving you more insight into how fast the tail probability of x is decaying. One thing to keep in mind is that there is no free lunch. If you go back to the original slides here, we need more assumptions on x to make Chebyshev's inequality work compared to Markov's inequality. Markov's inequality only requires you to have the mean. Chebyshev's inequality requires you to have the variance. So it's slightly more advanced knowledge of the random variable. But then that knowledge can be used to get a much better tail bound.